Okay, the next family we're studying is called amines. Now you'll notice the general formulas I wrote here: RNH2, RNH, R primed, and RN with R primed and R double primed. So again, the significance of the R primed, and R double primed is just that they're all hydrocarbon chains that can be of different lengths, and that's why the prime, to denote they don't have to be the same length. Okay, so you'll notice that all of these general formulas contain nitrogen, and that's what's new about the amine lesson. We build our amines, organic nitrogen-containing compounds, from ammonia. So you'll remember the formula of ammonia is NH3, and this structure of nitrogen with 3 hydrogens bonded. There is a lone pair of electrons, and that's really the last time you're going to see them. So in our structural formulas, just like with oxygen and the halogens, we don't show the lone pairs. But just as a refresher, here's ammonia. So amines are organic compounds built based on ammonia. We either replace one hydrogen with a hydrocarbon group, or 2 hydrogens, or even all 3 of the hydrogens. The functional group is called amino, an amino group. And again, if we have one of the hydrogens replaced, this is now classified as a primary amine. So just having a quick look up to the RNH2, you'll see there's an R group, a nitrogen, and 2 hydrogens. So here we go, an R group, a nitrogen, and 2 hydrogens. Yes, there's a lone pair here, we're just not showing it in the structural formulas. For the secondary amine, you'll notice that 2 of the hydrogens have been replaced. The third is still here. And in the tertiary amine, you'll see that all three of the hydrogens have been replaced with R groups. Regarding the physical properties, you'll see here that primary and secondary amines contain NH bonds. And perhaps I need to back up a bit here to look at that. So notice that the presence of the nitrogen-hydrogen bond means that adjacent molecules will experience hydrogen bonding. That's also true for secondary amines, although there's only one site for hydrogen bonding. You'll notice in the tertiary amine that there's no nitrogen-hydrogen bond at all, and so tertiary amines are not capable of hydrogen bonding. So we do see higher boiling points for these primary and secondary amines than we do for nonpolar hydrocarbons and even polar molecules that are not able to hydrogen bond with itself or themselves. So what would you predict then for the boiling point of primary compared to secondary amines? Both are capable of hydrogen bonding. Would you expect the boiling point of a primary amine to be greater than or less than the boiling point of a secondary amine? Hopefully you're thinking greater than, because there's a double opportunity for hydrogen bonding with the NH2 functional group. When you're comparing the boiling points of amines and alcohols, both are capable of hydrogen bonding, and so the question becomes, which bond is more polar? That greater polarity in the bond will set up a stronger hydrogen bond attraction between molecules. And so if you compare the electronegativity difference of NH and OH, you'll find that the OH is the more polar bond. And so we see those boiling points of alcohols being greater than amines, or as the way I've written it here, that the amines are less than the boiling points of the alcohols. And just to give you some data with that, here is a molecule that has 1 carbon and the amino functional group, and you'll see that the boiling point is -6 degrees Celsius. Here we have a 1 carbon alcohol. The hydroxyl functional group is present, and you can see that the boiling point is quite a bit higher. And so London forces are similar, and yet the increased polarity in that OH bond makes for stronger hydrogen bonds between methanol molecules, which raises the boiling point. A second point to be aware of is that as the hydrocarbon chain, the R group, increases in length, London forces will increase, and that will affect boiling point. So you'll notice here a 1 carbon amine, primary amine. And here we have 2 carbons in a secondary amine. Here we have 2 carbons in a primary amine. And here we have 3 carbons in a tertiary amine. So check out the boiling points here. We see -6, 7 degrees, 17 degrees, 3 degrees. That's interesting. So it seemed to be increasing, and we were seeing an increase from 1 to 2 carbons in this, comparing these 2 molecules. Now this one also had 2, but being primary, the structure of this allows for molecules to pack closer together. And so we see, and you'll understand that a little bit better when we explore shape in our second unit, but the primary amine can pack tighter than the secondary amine. So what's happening over here that this boiling point drops back down? Well, hopefully you'll notice here that the nitrogen is bonded to carbon in all 3 cases. These hydrogens are bonded to the carbons, not to the nitrogen. And so there is no ability for hydrogen bonding here. And so where we did have that earlier. And so that is going to lower the boiling point. Regarding solubility, it definitely depends on the ability to hydrogen bond with water and the size of those R groups. So remember, as with all our molecules, as the length of the R group increases, the nonpolar regions are becoming more dominant in the molecule, which will always lower the solubility in water. Okay, naming of amines. Now, this is a little tricky, so I think it's worth separating the compounds into primary, secondary, and tertiary amines. So I've gone through about 5 examples here for the primary amines. This does follow similarly to alcohols, aldehydes, carboxylic acids, and so on, where we wrote the name of the parent alkane, dropped the E, and added the suffix to the name. And so the suffix for amines is amine. If you're going to name the amino functional group as a prefix where a higher priority functional group is present, then you would need to call that group an amino side group. So let's take a look at example A, and following the same naming pattern that you've done before, name the parent alkane, drop the E, and add the suffix. Okay, so noticing that we have 1 carbon, we think monkeys, M stands for meth, so methane, drop the E, and add the suffix, so methanamine. Try B and C. So hopefully you're finding these similar to when we did alcohols. Really, there's a lot that's common. So in example B, 2 carbons. So monkeys eat, E stands for eth. We're thinking of the parent hydrocarbon as ethane. We drop the E and add the amine suffix. We're not numbering the location because if it's not on the carbon on the right, then it's on the carbon on the left, in which case we would number from left to right. Okay, in example C, you'll notice there's 5 carbons in the parent chain, so we're thinking pentane, drop the E. Now we need to number where that amino functional group is. Once you're past the 1 or 2 carbons, you need to number where it is, just like with the alcohols. And so we have pentan 2-amine. Now to do example D here, you'll notice that I've put 2 functional groups, the amino functional group and the chloro, the halogen. And so it matters, we need to revisit priority. So just to finish here, we see with priority, we see the carboxylic acids up top, then aldehydes, ketones, alcohols, and now the amines. So you'll see that the amines fall in group A, but they are below any of those oxygen-containing families. Double and triple bonds are still lower priority than anything in group A. They are in group B. And finishing out the lowest priority, and again these are all equal priority, just lower than anything in group A or B, we have alkyl, halo, phenyl, nitro, and alkoxy, the side groups associated with ethers. Okay, so give questions D and E a shot, and remember that if you are naming the NH2 as a side group, you use the name or prefix amino. Again, there has to be a higher priority functional group present in order for you to name it as an amino. In example D, you'll notice the presence of the amino and the chloro group. Looking at our priority list, the amino group is in group A and the halogen is down in group C, which means that we will name this molecule as an amine. And so we number to give that highest priority functional group the lowest possible number, which is why I'm numbering from left to right. So we finish with butane-1-amine. Where's the chloro group? Off of 3, and so 3-chloro-butane-1-amine. Now the difference with example E was that out of the two functional groups present, the carboxyl group is higher in priority. And so because the carboxyl group is higher in priority, it becomes the suffix. And so we name the NH2 group as an amino side group. And so we have 5-amino hexanoic acid. Okay, so for secondary amines, you'll notice that 2 of the hydrogens in ammonia have been replaced. And this adds a little wrinkle, a little new feature to the naming that we've been doing. So the parent chain is going to be the longer of the 2 R groups that are attached to the nitrogen. And so if I'm looking at example A, I see there are 2 carbons here and only 1 here. So the parent chain is the longer R group. That will be eth in this case, ethane, except we're going to drop the E and add the amine. And so we write here ethanamine. We don't need to number it because for 1 or 2 carbons we don't number. Okay, now we need a prefix up in front to indicate the other R group. And so this group here becomes indicated as capital N hyphen methyl, and that links right into, it's all one word, so N-methyl ethanamine. Why the capital N? Because that alkyl group is bonded to the nitrogen. So we're viewing this as the parent and the methyl group as the side group, if you will, something smaller bonded to the nitrogen. So check out question B. Here's another secondary amine, which means there will be 2 R groups. So the longer R group is your parent, drop the E, number the location if you need to. If there's more than 2 carbons, you need to number it, add your suffix. And then capital N with the alkyl group bonded to the nitrogen out up front. Okay, and so we have 3 carbons versus 1 carbon in our R group, so the 3 will be the root. So propane, drop the E. Because there's 3 or more carbons, we need to number where that nitrogen is coming off, so propane-1-amine. That leaves an N-methyl coming out front. Okay, and now for the tertiary amines. So all that's different here with the tertiary amines is that we will have 2 groups attached to the nitrogen in addition to the parent hydrocarbon. And so just as before, the longest R group will be the parent. So in example A, 1, 2, 3, 1, 2, and 1. So 3 is clearly the longest. Monkeys eat peeled. Peeled stands for prop. And that nitrogen is coming off the first, so propan-1-amine. Now what goes out front? Well, an N-methyl and an N-ethyl. And we do that in alpha order, and so I'll start with the N-ethyl hyphen capital N hyphen methyl, and that links right into the propan-1-amine. So you try part B and then check in. And so we have N-N-dimethyl ethanamine. Hopefully that makes sense to you that both R groups here being named as prefixes are in fact identical, and therefore we'll pull out the dimethyl. And we need to indicate 1 capital N for each side group or each R group here. So we have N-N-dimethyl ethanamine. Okay, last bit here refers to the reactions. And so you'll see that I've indicated on the side here substitution reactions, and that's the key. So we're going to prepare amines. In preparing these amines, we look at first ammonia, that inorganic reagent. When we react it with a haloalkane, I've tried to color code it for you, you'll see that the red H comes off and hooks up with the HX here, or the X, so we have HX, And in place of that red hydrogen, we now have the R group. And so it's alkylation in the sense that we're being able to substitute an R group in place of the hydrogen. And you'll see that that now forms a primary amine. So here's an example where you see the 3 hydrogens, and that red H is going to come off and go with the Cl. There's the HCl. And this R group is going to replace that H. Notice it's where the chlorine was attached, that's the carbon that attaches to the nitrogen. And so we formed a primary amine. In example B, I'm taking a primary amine and reacting it with a haloalkane. Now this R primed can be a different hydrocarbon length than the one that's already on the nitrogen. And you'll see that the hydrogen here and the X come together as a byproduct, and the R primed group replaces this hydrogen, and there we formed a secondary amine. Again, it's always substitution. So when we look at this example, we see the primary amine here, and that had 2 carbons in the R group. Now I have chloromethane, and the H comes off and the Cl form the byproduct, and then the CH3 replaces that H. And so we have N-methylethanamine, and here is our secondary amine. Finally, if we have a secondary amine, we can react it with another haloalkane. Again, it could be a different R group, and in doing so, a substitution reaction occurs again. Hydrogen comes off with the halogen, there's the HX, and the R double prime group replaces the hydrogen. And there we have the formation now of a tertiary amine. So does this look like a secondary amine to you? You see how there's 2 R groups coming off, right? 1, 2, and 1 here. Now in the haloalkane, you'll see there are 1, 2, 3 carbons. And so we're going to replace this hydrogen here with the R group. And you'll notice 1, 2, 3, there's our new R group. So make sure you add these reactions to your summary list and check out the next video on amides.